Hi everyone, I'm Honghu-Chu from Hunan University, and I'm now a visiting PhD student at UCL. Our research title today is Fine-Grained Segmentation of High-Resolution Break Crack Images using Rendering Technology. And this work is co-supervised by Dr. Weiwei Chen from UCL and Professor Deng from Hunan University. Now let's get started. My talk is organized by the following components. Let's start with some background information collected in Europe and China. The volume on bridge infrastructures is huge, and around 34% of the bridges in those regions are more than 50 years old. And the picture down below shows that in both regions, the bridge, over 10% of the bridge are in poor condition. So the government required the regular inspection to ensure the bridge safety. In terms of the cost of the inspection and maintenance, the total expenditure is over 25 billion per year, which is a huge investment reflecting the importance of bridge safety and bridge inspection. As we all know, among all the inspection process, the crack inspection can be treated as one of the most important ones. If the crack cannot be effectively detected, it may lead to some horrible disasters like what happened with the Xinhai Bay Bridge and the Nanfang Bridge showed on the picture. Traditionally, the crack inspection have been done manually. Here I'll give some examples like using the under-deck gantry inspection barge, rope access, and the bucket trucks to get the inspector to be close enough to the structure surface to have a good look of the crack. But this method are high cost, risky, labor intensive, and will cause traffic disruption. Now, with the development of unmanned vehicle and deep learning methodologies, some modern solutions were proposed. Here I'll give two typical examples. One is the ring-type climbing robot combined with the thicknet for the bridge pier crack inspection. And the second is the unmanned vessel combined with the center net for the under-deck crack inspection. But these devices are poor flexibility and has to be customized for each specific project, so they are very expensive. In contrast, the UAV has its advantages in high flexibility and can be used to conduct the crack inspection for almost all the bridge components. So it was treated as one of the most promising solutions for replacing the manual inspection these days. But when performing the UAV-based bridge crack inspection, as shown on the picture, the UAV can easily crush with the bridge. Since there's always strong wind on the bridge site. To avoid this risk, we commonly have two solutions. Solution A is just upgrade the UAV's hardware, which means we can develop more stable flight control systems. And the solution B is a direct way. We can increase the detection distance, just keep the UAV a greater distance away from the bridge surface. Obviously, the solution B is a much more economical solution that we can adopt. As the distance between the UAV and the bridge surface increase, some challenges also arise. That is, the crack image captured by the camera become blurry. This is because the cracks objects in the image following the imaging principle, which is the farther the shooting distance, the smaller the size of the crack in the view. That will lead to the loss of fine details and the crack edge elements. So our goal becomes to develop some recognition algorithms to ensure that the tiny crack can still be accurately detected when the shooting or the inspection distance increased. So we got the inspiration from the field of computer graphics. We found that the blurring of crack boundary and the loss of some tiny details are similar to the aliasing effects in computer graphics. And we found that the point-to-rand architecture proposed in CBPRN is one of the most advanced anti-aliasing algorithm in computer graphics. It used the rendering technique to refine the presentation and representation to the object details. The figure down below shows the workflow of the point-to-rand architecture and its visualization results. Compared to the traditional mask CNN, we can find that the point-to-rand can provide the mask with more refined details, especially in the boundary region. So we want to fully explore the advantages of this architecture to the meticulously representation of high-resolution crack images. But when we directly apply this architecture for the high-resolution crack image segmentation, some limitations also occurred. That is, we found the segmentation results still exhibit inaccuracies, especially in the crack boundary regions, and some tiny crack detail branches still lost. And then we figure out that the reason is that the original architecture used the cross mask for guiding the sampling points. This is because the crack object is quite different from the nature sense objects. It's very small, so in the cross mask, there's already lost some tiny crack details and the boundary details, making it impossible for the rendering point to be sufficiently guided to those ambiguous regions so that we cannot achieve refined segmentation results at these regions. So after figure out the problem's reason, our problem becomes how can we effectively provide sufficient crack detail information for the rendering point guidance for the point-to-rand architecture. Here we give our solution. We proposed the crack boundary point rendering network on the basis of the original point-to-rand architecture with two main innovations. The first is that we proposed a boundary branch, like showing the picture. And the second, we replaced the cross mask with the refined guidance source. Specifically, for the training phase, we used the pixel level labels for guiding the rendering points. And for the inference phase, we customized a probability heat map for the rendering point guidance. Now, let's have a close look about the first innovation, the age-guided branch. As shown in the picture on the right, it was composed of two main components. The first is the age detector, the canny age detector, which can be used to enhance the representation of crack boundary in the length feature. And then is a super resolution reconstruction encoder, which composed of series of Swan transformer blocks. And it can be used to restore some tiny crack details in the length features. By the combination of these two components, we can generate the network can generate the high-dimensional lantern feature with the refined edges and the tiny crack informations. And next, move on to the second innovation, the refined guidance source for rendering point guidance. For the training phase, as we mentioned before, we use the pixel level labels for the rendering point guidance. This is because the pixel level labels have the accurate age and the tiny crack information. And more importantly, it can be easily obtained in the training data sets. So when we directly use this label for the rendering point guidance, we can significantly reducing the training costs. Meanwhile, we can keep a very high level accuracy. And for the inference phase, things we cannot directly obtain the meticulous pixel level labels, so we customized probability heat map based rendering point guidance. Specifically, we defined the potential area of those boundary and the tiny crack branch ambiguous regions on the probability heat map. And all the rendering points will then be focused on these self-defined regions. By focusing the computational power to these ambiguous regions, the accuracy of these boundary and the tiny crack branch regions can be effectively improved. After the introduction of our innovation, let's move on to the experimental and the results section. Here are the data sets we used for the model training and the model evaluation. And 3 commonly used evaluation metrics, including the intersection over union, DAS, and especially the mean boundary accuracy was used to highlight the performance in boundary accuracy enhancement. First, we conduct a parameter experiment for the rendering point guidance in the training phase. For the training phase, here we can see on the picture, we test 4 different boundary widths on the pixel level labels to represent the region that needs to be meticulously represented by the rendering points. And we found when the boundary width is set to 5 pixels, the model performed the best. This is because the manual labeling bias is just happen to fall into these regions. And then we conduct the parameter experiment for rendering point guidance in the inference phase. In the inference phase, we self-defined 9 different probability ranges on the probability heat map to represent the boundary region that then need to be refined representation by our rendering points. And we can see from the table that the result shows when the probability range represented to the boundary region and the tiny crack branch regions is set to 0.3 to 0.7, the model performed the best. After demonstrating and finding the optimal parameter of the proposed method, we conduct a parallel comparison with the traditional point rand architecture. For the cross-segmentation, for the cross-mask generation, we use some cross-segmentation architecture, including the FCN, UNet, DeepLab-v3+, PSPNet, and the RefineNet. And we can see that after refinement by the point rand architecture, the quality of each cross-mask improves at almost the same level, but still not that good, especially in the crack boundary areas, and some tiny crack branches are still lost. And compared to the proposed CBPRN, we can find after the refinement by our method, both the crack boundary and tiny crack details can be finely represented. After the visualization results, the quantitative performance further demonstrate the visualization results is that we can see on the last line, the CBPRN use a more precision probability map than the cross-mask, so it can reaching the highest accuracy performance, and because it can be effectively guiding the rendering points, it also got the fastest inference speed on 4K resolution images. And finally, move on to the conclusions part. We've developed a new architecture named the CBPRN, and it can be treated as the first rendering technical-driven crack segmentation network, and especially designed for the high-resolution crack refined segmentation. It has high segmentation performance and can be treated as a universal solution when we want to design or build a architecture that especially for the high-resolution crack image segmentation. And for the implications, we provide a safer and a more accurate solution for the UAV-based breach crack inspection. In the future, we plan to develop some model tuning and quantization algorithms to achieve the lightweight deployment on the UAV in engineering practice for doing some more breach inspection project. Meanwhile, we want to explore the multimodal fusion technique to enhance the model's robustness in the real environment. Here are some of the key references that support our research. And thank you for listening.
Thank you. Thank you.